Welcome to the Explainer. When we talk about climate change, we usually picture melting ice caps or slowly rising sea levels. But today, we're diving into something way more immediate. And honestly, a lot more violent. We're going to unpack the exact mechanics of why scientists are issuing such urgent warnings about Nepal's glaciers and the really catastrophic risks this poses to the communities living right below them. Together, we're going to break down the physics, the geography, and the technology surrounding one of the absolute most pressing environmental threats in the high mountains today. We've organized this explainer into 5 key sections. First, the heating Himalayas. Then we'll break down the anatomy of a glacial collapse, map out Nepal's high-risk basins, look at the forecasting challenge, and finally, mitigating the glacial threat. Let's get right into it.
All right, Section 1, the heating Himalayas.
So, the most striking thing glaciologists want us to know right out of the gate is this chilling warning. What we recently saw happen in central Nepal, it's gonna happen again. It is definitely not a one-off event. With temperatures accelerating across the Hindu Kush Himalayas, these frozen mountain slopes are actively destabilizing, which makes future ice rock avalanches basically an absolute certainty. And here is a number that just completely blew my mind. 2. The Himalayas are warming at almost double the global average rate. Double! When you think about what that means for a landscape that is defined entirely by ice, it's incredibly alarming. This extreme heat is rapidly thawing out the high-altitude permafrost, which fundamentally changes the structural integrity of the mountains themselves. To really wrap our heads around this, we have to realize that permafrost isn't just a layer of ice sitting on top of a rock. It actually acts as the crucial structural glue holding steep mountain bedrock and massive, heavy suspended glaciers together. So as temperatures rise, that frozen glue literally just degrades away. And what you're left with are thousands of steep, hanging glaciers perched on sheer rock faces, totally unsupported, just waiting for gravity to do its job.
Which brings us to Section 2, anatomy of a glacial collapse.
Okay, before we get into the physics of the bedrock snapping, we've got to talk about GLOFs, or glacial lake outburst floods. See, as glaciers melt, they create these huge, expanding lakes. And those lakes are held back by super fragile dams made of loose rock and debris, called moraines. GLOFs are these deadly, massive floods that happen when those fragile dams suddenly burst. This usually happens because an avalanche crashes into the lake, or heavy rain just completely overloads the system. So how does one of these disasters actually unfold? It's basically a 3-step process. Step 1, the slow, totally invisible permafrost thaw that forms deep cracks in the ice. Step 2, a massive bedrock shear where the mountain literally just gives way. And Step 3, a super rapid debris flow rushing downstream. What makes this so incredibly dangerous is the lead time. Once Step 2 happens, downstream communities might only have minutes, maybe a few hours if they're lucky, to react. And this is where the physics gets completely wild. When those suspended glaciers finally snap, you've got millions of tons of ice and rock free-falling for thousands of meters. The sheer dynamic impact and kinetic friction from that fall generates so much heat, it instantly melts huge quantities of the falling ice. So it starts as a solid avalanche, literally weaponizes in midair. It turns into this high-speed, liquid slurry of mud, water, and boulders, sometimes tearing down a valley at highway speeds of over 60 miles per hour. Let's move to Section 3, Nepal's high-risk basins. When you look at the different threats across Nepal, you really see how much the local geography dictates the danger. It's not a uniform threat at all. For instance, in the Trishuli and Bote-Koshi basins, you've got steep valleys where those ice rock avalanches directly threaten border infrastructure and hydropower plants. Over in the Koshi basins in the east, the main threat comes from expanding glacial lakes hanging right over agricultural valleys. The Gandaki Basin is dealing with permafrost thaw, threatening cities, while the extreme slope angles in the Kali Gandaki create these severe debris flows that can completely block rivers and wipe out major highways. And to give you a sense of the scale we're dealing with, there are over 200 expanding, highly unstable glacial lakes right now across Nepal. 200. And they feed directly into these exact basins. Every single one of them is a potential mega flood just waiting to be triggered by the next avalanche. Now, on to Section 4, the forecasting challenge. So you might be wondering what scientists and vulnerable locals are asking every single day. With all our modern technology, why can't we just predict these massive structural failures before they wipe out a valley? Well, think about it like a volcano. Volcanoes usually give us some measurable warning signs, right? Magma shifts, the ground bulges, we get seismic tremors. But glacial bedrock fractures? They are practically silent. They lack distinct early warning signals, meaning there are almost no remote indicators before the catastrophic failure suddenly happens. That structural glue we talked about earlier just silently lets go.
Because of this, scientists are stuck trying to monitor thousands of mountain peaks all at once with very limited detection capacity. It's literally like trying to find a single snapping branch in a massive forest. But what turns this natural hazard into a true crisis is the human element. Systemic vulnerability is rapidly increasing because of unregulated road and hydropower construction happening right in the floodplains, sitting squarely beneath these invisible, silent hazards.
Okay, finally, Section 5, mitigating the glacial threat.
So what are the actionable steps we can actually take to adapt and protect people? First up, we absolutely have to deploy automated early warning systems, things like seismic sensors and water level telemetry along these vulnerable river channels. We also need to lean into space tech, utilizing synthetic aperture radar or SAR satellites, which can track tiny ground shifts on high-risk slopes from orbit. But technology alone isn't going to save us. We need strict floodplain zoning to literally stop building things in the path of destruction. And crucially, we need better transboundary data sharing across the whole Himalayan arc, because these massive floods certainly don't respect national borders.
As we wrap up this explainer, I want to leave you with something to really ponder. The current climate trajectory tells us that these high mountain instabilities are 100% guaranteed to rise. Since the mountain's structural glue is irreversibly melting at double the global rate, our safety relies entirely on human adaptation. So the big question is, are we moving fast enough? Will constant monitoring and strict floodplain management actually be enough to outpace the heat? Or are we just continuing to build right in the crosshairs of an inevitable collapse?